Deep in our solar system, there's a world shrouded in mystery. Its orbit brings it close to a blazing star. A thick veil of clouds has always hidden its true face. Ancient myths and untold stories have surrounded this planet for thousands of years. Its atmosphere holds countless secrets, like whispered warnings from another age. For decades, brave spacecraft have crossed the cold void of space, trying to pull back the curtain on this enigmatic world. Venus, our evening star, our sister planet. In size, it's remarkably similar to Earth, but it sits about 40 million kilometers closer to the Sun, making it the second planet in our solar system. For millennia, Venus has inspired myths and legends across every culture on Earth. But in recent decades, our understanding has gone far beyond. Watching it glow as a bright dot at dawn and dusk. At the height of the space race, dozens of robotic probes were sent to observe Venus, orbiting it, flying through it, even landing on it. Using instruments that could detect visible light, infrared, and ultraviolet radiation, we began to uncover a world that differs from Earth in nearly every way imaginable. Venus is the second brightest object in the night sky, surpassed only by the Moon. It has always drawn the eyes of anyone who looks up, but even today, getting there remains a serious challenge, let alone during the Cold War. Between 1961 and 1967, of the first 15 missions sent to Venus, only 3 were considered successful in achieving their specific goals. NASA's Mariner 2 and Mariner 5, and the Soviet Venera 4, 5, and 6, which successfully entered Venus's atmosphere. Then, in late 1970, the Soviet Union's Venera 7 changed everything. It became the first spacecraft to land on another planet and survive long enough to transmit data back to Earth, a landmark moment in the history of space exploration. Now, let's follow one of those probes on its journey through Venus's atmosphere, all the way down to the surface. The probe launches into space and begins its descent toward Venus. The upper atmosphere opens up before it, stretching from the edge of space at roughly 250 kilometers, down to about 60 kilometers above the surface. At this height, there's only a thin, wispy haze. Nearly 99% of Venus's atmospheric mass lies below, and passing through this layer is relatively easy, similar to traveling through Earth's atmosphere at the same altitude. But the chemistry is already different. Instead of nitrogen and oxygen, the probe begins detecting traces of carbon dioxide. At this height, the concentration isn't enough to significantly affect temperature, but it's a hint of what's coming. In terms of broad behavior, the upper atmosphere of Venus at this altitude is similar to Earth's, with large temperature swings between day and night. Daytime highs reach around -37 degrees Celsius, while nighttime lows drop to around -113. For the probe, this layer is still manageable. Worth noting, beyond the carbon dioxide, there are oxygen atoms here that emit infrared radiation, detectable by telescopes and spacecraft instruments. In images captured by the Venus Express Orbiter in infrared wavelengths, the blue tones are caused by these oxygen emissions high in the atmosphere. As the probe continues downward, it enters the main visible cloud layer, around 60 kilometers above the surface. The dull yellow color we see in visible light photographs of Venus comes almost entirely from these clouds. In this part of the atmosphere, ultraviolet radiation from the sun breaks carbon dioxide down into carbon monoxide and individual oxygen atoms. Those oxygen atoms then readily react with sulfur dioxide and water vapor to other trace compounds in Venus's atmosphere, producing the sulfuric acid clouds that define Venus's appearance. This is the calm before the storm, a deceptive stillness before the probe descends into something far more hostile. The surface of Venus cannot be seen through its thick cloud cover, so the probe must descend completely blind. Those same clouds reflect about 3/4 of all sunlight that strikes Venus. The suspended crystals of sulfuric acid are highly reflective, and that reflectivity explains a great deal of why Venus appears so brilliantly bright, both to passing satellites and observers here on Earth. Remember, it's the second brightest object in the night sky. Looking at those mustard yellow clouds in visible light, they appear thick and impenetrable, with no hint at all of what lies beneath. But we have something probes don't: infrared sensors. In infrared, things look completely different. Images captured by the Venus Express spacecraft reveal clear, bright, and dark patches across the atmosphere. What we're seeing is the dense concentration of carbon dioxide filling the lower atmosphere. Carbon dioxide is a powerful greenhouse gas. It traps heat from the sun and drives the extreme surface and atmospheric temperatures Venus is infamous for. In infrared, this becomes completely unmistakable. The entire surface glows with heat, trapped beneath the thick CO2 layer. The darker patches and streaks are those sulfuric acid clouds, sitting high above the hotter CO2 layer below. Can you imagine what the probe experiences as it pushes through all of this? Sulfuric acid attacks its outer shell. Winds tear past at 100 meters per second, 60 times faster than the planet itself rotates, fast enough to circle the entire planet in just 4 days. Temperature at 50 to 55 kilometers altitude ranges from 25 to 75 degrees Celsius, then climbs rapidly toward the scorching surface below. Air pressure at Venus's surface is 75 to 100 times that of Earth at sea level, the equivalent of being nearly a kilometer underwater. It's like having an entire car resting on your fingernail. And as the probe descends further, things get stranger still. Once it punches through the sulfuric acid cloud layer, the air clears again. But the conditions here are unlike anything on Earth. The pressure is now so extreme that it begins to affect the carbon dioxide itself. At this level, CO2 becomes so dense that it no longer behaves like a gas in the traditional sense. It enters a supercritical state, a phase of matter between liquid and gas, sharing properties of both simultaneously. Here, the winds have slowed dramatically compared to the chaos of the upper cloud layer. Near the surface, wind speeds drop to no more than 5 kilometers per hour. But don't let that fool you. Moving through this dense atmosphere would feel like wading through a slow but unstoppable current in a river heated to 464 degrees Celsius, hot enough to melt lead. Modern technology can tell us a great deal about these atmospheric layers. To illustrate just how intense the heat is at this depth, look at images of Venus's lower atmosphere captured by the Galileo spacecraft in near-infrared. The superheated red regions of the lower atmosphere are unmistakably visible. The darker patches caused by the sulfuric acid clouds higher up are clearly visible too. Venus's lower atmosphere is extremely hot, with distinctly different layers, varying dramatically in both temperature and chemical composition. To further highlight those differences, let's look at Venus in ultraviolet. Images from the Venus Express spacecraft at wavelengths of 283 and 365 nanometers don't show quite as much contrast as the infrared images, but they reveal far more variation than visible light alone. The dark regions and patches in the clouds indicate areas where ultraviolet radiation is being absorbed rather than reflected. But exactly which chemical or combination of chemicals is causing that absorption? That remains a genuinely open question in planetary science. Clearly, there are still compounds in Venus's atmosphere that have so far eluded our attempts to identify and classify them. On that subject of hard-to-explain features, here are infrared images of Venus's poles. Notice anything unusual? At both the north and south poles of Venus, there are massive vortices, each roughly the size of Europe, driven by winds of 100 meters per second. What makes them truly strange is that each one has a double center, not one eye, but two. Scientists still aren't entirely sure why. Venus's complex, highly variable polar vortices are extremely difficult to model because they can change on timescales of less than 24 hours, making them one of the planet's most persistent mysteries. But once a probe survives that mysterious atmosphere and finally touches down in that hellish environment, what does it actually see? Let's complete our descent through the dense acid clouds and reach the surface of our nearest planetary neighbor, because the dense sulfuric acid clouds block any line of sight from space. The only photographs showing Venus's surface in visible light are those taken by landers on the surface itself. Of those images, we have just 6 from Soviet Venera landers that successfully touched down. And what's surprising is that images like those from Venera 9 are unexpectedly clear. Scientists had assumed the dense atmosphere would scatter all light into an impenetrable haze, but that turned out not to be the case. Everything has a dim, yellowish tone, a result of the acidic atmosphere filtering the light. And while you might be surprised to find solid rocky ground beneath Venus's crushing pressure, that ground tells a story, hinting at ancient lava flows, now hardened into flat plains, weathered by Venus's brutal environment. Everything looks extremely dry. Given the scorching heat, that's no surprise. Perhaps it's a preview of what Earth itself might look like in billions of years, if the sun's increasing luminosity triggers a similar runaway greenhouse effect. But here, we must leave the probe behind. Every Venus lander, including the ones we've been following, survived on the surface for no more than a few hours before succumbing to the heat and crushing pressure. Their images gave us brief but vital windows into that rocky alien terrain. Still, those images from 40 years ago are the only photographs ever taken from Venus's surface. But there's another way to understand Venus's geography, one that doesn't rely on visible, infrared, or ultraviolet light. None of those can pierce the cloud cover clearly enough to map the surface. For that, you need something entirely different: radar. The Soviets began radar mapping of Venus's surface in 1983. Their later Venera 15 and 16 missions produced surface images with a resolution of 1 to 2 kilometers. That effort was taken significantly further about a decade later by NASA's Magellan spacecraft, which between 1990 and 1992 managed to map approximately 98% of Venus's surface at a resolution of 120 meters. The images produced from that radar data are genuinely spectacular, revealing massive volcanic structures, large-scale impact craters, and a surface that appears geologically young, likely reshaped by intense volcanic activity that produced enormous lava flows across the planet. The composite surface maps created from Pioneer Venus and Magellan mission data are stunning. From volcanoes to valleys, impact craters to fault lines, the surface detail is remarkably clear. Radar imaging can pierce the clouds and reveal the hidden beauty of Venus's surface, greatly expanding our understanding of this planet. So when it comes to our nearest planetary neighbor, what does the future hold? The biggest Venus news in recent years was undoubtedly the announced detection of phosphine gas in Venus's atmosphere. Measurements from the James Clerk Maxwell telescope appeared to show traces of this compound. Phosphine can be produced through various natural processes, but one of them, and the one that caused genuine excitement, is production by microbes in low oxygen environments. Life in one of the most unlikely, hellish places imaginable. That would have been an extraordinary discovery. However, follow-up studies failed to confirm the phosphine detection. By 2022, NASA had largely dismissed the idea of phosphine being present in Venus's atmosphere, concluding that the original results were likely an error. But then, Professor Jane Greaves of Cardiff University announced at a major conference in 2023 that the James Clerk Maxwell telescope had detected it again, this time in Venus's lower atmosphere. Hopefully, future missions will give us a definitive answer to this truly tantalizing question. There are many other open questions still waiting to be answered. Why did the planets, Venus and Earth, so similar in size, evolve so differently? Was there ever liquid water on Venus's surface? What does the precise chemical profile of Venus's atmosphere and surface actually look like? And what might higher resolution surface images reveal? Could they help solve these puzzles? After decades of relative neglect, with attention focused on Earth orbit and the outer planets, Venus is suddenly exciting again. In the coming decade, several missions are set to launch toward Venus from the United States, the European Space Agency, Russia, China, and even a private American venture called Venus Life Finder. Hopefully, one or more of these missions will take us on a great journey of discovery, answering some of our most pressing questions about this fascinating world. By observing Venus across multiple wavelengths, we gain far more than visible light alone can offer. We can peer through kilometers of opaque cloud to map volcanoes and impact craters, identify parts of the atmospheric and surface chemistry, and use infrared imaging to make the invisible visible. All of this gives us valuable clues about why conditions there are so extreme, and perhaps, just perhaps, whether simple microbial life might exist on our nearest neighbor. As technology continues to advance, we may one day finally lift the veil from Venus's deepest secrets. There's also an idea, unverified and without scientific support, that humans may have once originated on Venus and migrated to Earth following some catastrophic ecological collapse there. There's no confirmed evidence for this, but it's an interesting thought to sit with. What do you think? Leave your thoughts in the comments below.